CERN's Large Hadron Collider could be generating dark matter in its particle jets. If dark matter is made from dark versions of the basic building blocks of ordinary matter, the world's largest particle accelerator, which is in Switzerland as we know, should be able to pin it down, a new study suggests. A new research for dark matter has turned up empty-handed, but in a silver lining, the effort provided important limits that will help future experiments narrow down the hunt for this elusive substance. Most astronomers believe that dark matter accounts for 85% of all mass in the universe, and that its existence could explain the apparent extra gravity detectable around galaxies and within huge galactic clusters. However, so far no one has been able to identify what dark matter is made of. Until recently, the front-runners suspected that had been a breed of particle called WIMP, W-I-M-P, which is a neat acronym for weakly, that is not strong, weakly interacting massive particles. These theoretical particles are thought to barely interact with normal matter, except when it comes to gravity. However, the Large Hadron Collider, the world's largest and most powerful particle accelerator, the LHC, has failed to turn up evidence of the existence of WIMPs. Thus, theorists are having to scramble to find alternative theories of what dark matter could be. WIMPs is one class of particles that are hypothesized to explain dark matter, as they do not absorb or emit light and don't interact strongly with other particles. Deepak Kar, professor of physics of the University of Witwatersrand in Johannesburg, South Africa, said, however, as no evidence of WIMPs has been found so far, we realize that the search for dark matter needed a paradigm shift. So alternative methods, some of the methods of dark matter posit that rather than being weakly interacting, dark matter could actually interact strongly with some particles in the Standard Model, which is a framework of particle physics that describes every known particle as well as how each particle interacts with and relates to one another. Dark matter particles are believed to exist beyond the Standard Model scope. The models that predict strongly interacting dark matter rather describe an entire menagerie of theoretical particles, starting with basic dark quarks and dark gluons. Those are like dark mirrors of quarks and gluons that are the fundamental building blocks of all visible matter and surely present in the Standard Model. Now Kar and his former student Sukanya Sinha, who is now at the University of Manchester in the UK, have developed a new way of searching for these potential dark quarks and dark gluons in high-energy collisions between protons that take place within the Large Hadron Collider. When protons come together at almost the speed of light inside the LHC, they are smashed apart into their component quarks and gluons that swiftly decay to produce a shower of short-lived subatomic particles, and these particle showers are referred to as jets. Kar and Sinha's idea, which formed the basis of Sinha's PhD, is that possible dark quarks and dark gluons could decay to produce a mixture of particles, some ordinary and some dark as well. This would result in what they refer to as semivisible jets. Jets are produced in pairs, they explain, and if one normal jet and one semivisible jet were produced side by side, the dark particles would carry away some of the energy, leading to a telltale energy imbalance reading because the dark particles would not be seen. Kar and Sinha have led a search for these energy imbalances with the LHC's ATLAS experiment, because a slight mismeasurement of two normal jets could mimic the energy imbalance of a semivisible jet. However, the data from ATLAS had to be analyzed very carefully. And the duo found no evidence for semivisible jets, but that does not mean they do not exist. The ATLAS results, published in the journal Physics Letters B, point to upper limits for the properties of these theoretical dark particles, allowing future experiments searching for them to be fine-tuned. This was originally posted on space.com, and it's on Live Science. by Keith Cooper. Please leave your comments. Thank you for your support. Support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.